And now you can unmute yourself.
Yes, sir. Thank you, sir. Sir, fine, sir. Thank you.
I hope you benefit from the lectures.
Yes, sir.
Welcome, sir.
Hello, how are you?
Fine, fine. How about you?
Yeah, I'm good, thanks. Just finishing my normal office hour.
Right.
There are a number of meeting today, so I feel tired. Like with online, office environment,
Yeah.
the
Yeah.
frequency of the meeting have increased significantly.
Frequency and length also.
Yeah, length of yeah, you're right, because it's very easy to organize meeting.
Yeah.
um,
And you cannot say no also. In physical, you can say no.
um, yeah, um, most of them, relevant to your work commitments, so sometimes it's difficult to say no. Yeah. So your semester is running now. Our semester will start.
Our semester is uh, in the country, actually different universities will work with different academic calendars. But
Oh, okay.
in our case, we have started on January 1, 1st Jan.
Okay,
We have
okay.
started. So let's see. Now in Feb, by the time this course ends, we should be having our mid exams somewhere.
Okay, okay. For our case, I mean, the starting time almost fixed every year, like the autumn and spring semester. So we start like end of February for
Okay.
autumn, and spring we start like end of July.
End of July.
Yeah.
So and then end of July to.
End of November.
So you have got a big space between November to February, like 3 months.
Yeah, I mean that's mainly we utilize that time for research.
Okay, okay.
And also, I mean, nothing happened actually from middle of December to middle of January.
Yeah, that's
Because,
Christmas season also is there.
yeah, because that's the main holiday here.
Yes.
All the people they,
Okay.
go for holiday. So yeah.
We have got one more new participant today.
Okay. Hopefully he can catch up.
Yeah, I have shared the material.
Although I mean I sent, but again, I mean when you want to just revise your slide, always you think that something to add. So anyway, I mean I did make some changes, but I'll share the updated one again.
Okay, okay, fine.
What was the normal like duration? I mean in your class, is it 1 hour or 2 hour?
No, that's 1 hour. 1 hour.
1 hour.
Yes.
Okay, okay.
I believe 1 hour is optimal actually. At least in a one-to-one.
That's right. I
In
mean,
in
2
a
hours
physical
sometime.
class, 1 hour is optimal.
Yeah, I mean, 2 hours sometimes student feel tired as well as lecturer as well.
Two hours may be good, like when you are very much enthusiastic. 1 or 2 days, it appears to be very good. Then over a period of time, if the same person is teaching for 3 months to you, and if you study for 2 hours a day, it becomes a little bit
That's right.
problematic. In 1 hour, you have got like 10 minutes to conclude, 10 minutes to start off. So plenty of and still plenty of time is left. 40 minutes is good enough.
Yeah. Because I think there have been many research that, I mean, your brain can continuously at maximum like 15 to 20 minutes. So
Yes.
that's how
That is
you
what.
should you should change your activity like in every 20 minutes.
No, that is what even I heard somewhere in online pedagogy. Not only online pedagogy, but otherwise also. 15 minutes is the optimal time for concentration. After that, the concentration lapse happens.
Yeah. Online even is more difficult than face to face. Because online you have got
Yes.
so many device with you, right? So
Yes.
it's very easy to um, just
Beautiful
lost your
music
concentration.
also. Something, yeah.
And
In offline, at least you are forced to sit there and to listen.
yeah, that's right. And here you have got mobile, it's always making tung 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 sound, different app is on. When something is coming up, then always wants that, let's see what is there.
And sometimes even what is happening is, I'll tell you, you need two computers to take an online class also. In some cases.
Yeah.
So I do log in with two PCs, and then you change the host, the screen from here, sharing from here, then sharing from there. But
Yeah.
there are so many side effects. On online, you can go too fast, and
Because you cannot read your student, because when have like face to face,
yeah,
it's easy to read your student, like whether they are understanding
right.
your concept or not. But
Right.
online is very difficult, and most of the time student turn off the video even if you don't know what they are doing.
Right. No, in some
Don't
cases,
know.
in some cases, you have to ask them to turn off the video because the bandwidth required is too high.
That's right. And even if you ask them, sometimes they will say that there's some issue with their microphone bandwidth and
Yes,
so on. So
that is always there, and you cannot catch them also.
no, you cannot catch them, you cannot force them. But anyway, that's the world probably we have to live with in coming years, because many universities, they think like they will continue some activity online.
No, this is going to be the norm, I think so. Like,
Yeah.
and this will be helpful. Like, if we want to interact with people like you, online is an easier way.
Yeah, that's right.
We can start. I think so. We have 20.
Okay. We can start now. Just let me share my slide. So Altaf, can you just confirm me whether you can see my slide and also
Yes,
you can
yes.
hear me clearly?
Yes, both are okay. We can view as well as hear you.
Okay. Again, welcome everyone. So yesterday, we started photovoltaic system. So initially, I talk about the photovoltaic system working principle, mathematical models, and then impact of temperature, shading on the performance of only the photovoltaic panel. But as you know that, like when you're thinking about the photovoltaic system, it's not only photovoltaic panel, but it includes other devices as well. Now here, you can see a complete photovoltaic system, which actually include number of devices. For example, here, this is our panel, and then you have got DC to DC converter, then you have got inverter. So in your home, I think you might have DC load. If there's a DC load, you can directly connect after the DC to DC converter. And as you know that most of the load are AC, so we need to convert from DC to AC, and that is being done with inverter. And here you'll get AC, and then you can connect with your AC load, and also it can be connected with the main grid as well. Now, as you know that the photovoltaic output is DC, but still we need another DC to DC converter because it is like, unregulated from the photovoltaic system that voltage you are getting. You cannot control depending on the radiation and panel, you will be getting the DC. But if you want to control the DC, I mean, you need the DC to DC converter, and also sometime to get the required voltage here, sometime also you need to slightly bit boost up the voltage. So you can also do sometime DC, I mean, from DC to DC converter. And as I mentioned yesterday, that we need to always operate that photovoltaic system at maximum power point, and which is done by maximum power point tracking control, which is actually achieved through this DC to DC converter. So here you have got MPPT control that we already explained yesterday. And then we also have got control for the inverter, which I mean few control I'll just explain quickly today, because as you know that, I mean, when you are going to design control, I mean, always you need mathematics. So, and most of the cases, I mean, those mathematical model are widely available in the literature. So what we need to know that, how we can utilize those equation and then design the control. And for control also, there are so many techniques available in the literature. So based on your, I mean, requirement, probably you need to find out, which one would be the best for a particular application. So I'll just, explain a few control technique briefly. And then you also know that, I mean, not every PV system has got energy storage with them. But definitely, I mean, if you want like isolated off grid, then I think there is no option that you must have, some sort of storage technique with your photovoltaic system. Otherwise, you won't be able to run or power your load for, entire 24 hours. If it is grid connected, it's fine. Without battery, I mean, you can use, and the remaining you can sell to the grid. But if the grid is not there, then you must need the energy storage system. And for energy storage, I mean, you know that we need a bidirectional converter because you want to both charge and discharge. So what I mean, I'll be doing that. I'll explain like, how you can actually design a simply a photovoltaic system based on your own requirement. But before that, I mean, can I just ask a simple question? Is any of the attendees here, do you have a photovoltaic system in your rooftop? Yes or no?
No, sir.
No, we don't have. Still
I don't have it, sir.
No, sir.
Okay, no, that's fine. Because EPS, I mean, I just would like to ask, like, when you buy that, photovoltaic system, how you have decided, like, what size of all the equipment that's probably, you have decided. Because in most of the cases, I mean, what happened, like, if you ask that, like, that the supplier, so based on their interest, probably they will design the system. Sometime, I mean, they would like to make it cheaper if someone is looking for a cheaper option, and sometime, they can make it even costlier than, I mean, the actual cost needs to be. So that's why if you know, like the way that we can design the system, and what sort of size we need based on my own energy demand. So and that process is very simple, and I'll explain how you can do it. This is not only for designing your own system. If you would like to analyze PV performance, or if you like to even to show the impact, and for example that one that Ibrahim shown yesterday. So when he was talking about different PQ control, power factor, and so many control. So all of them are actually the controlling this inverter. Because here we don't have any control over the photovoltaic system. So the main control that we can do mainly for the inverter. So either to minimize grid impact or to provide any ancillary service to the grid. So the main component that we can utilize, that's the inverter. Now, let's say how you can firstly, if it is like a off-grid system. For example, let's say you have only your home and you would like to design a photovoltaic system which is not connected with the grid. So to do that, how you can do that? So the first step that you need to know your consumption demand, like in your own home. Like first you calculate how many appliances you have. For example, that lighting load, your refrigerator, your air conditioning, dishwasher, washing machine. So all of these appliances is not difficult to find out their power rating. For example, how many kilowatt their standard their ratings, and on an average how many hours you utilize per day. So here actually what we need the energy, and as you know that when you have got power and the number of hours that you are utilizing, so you just multiply that watt or kilowatt, the rating, with how many hours you are using. That will give you watt hour or kilowatt hour, and that's actually the energy you need to know. And once you know, like on an average, per day energy demand, from that you would be able to calculate what sort of panel size you need for your own houses, or it could be from any commercial or even like residential building. Now, just to be safe side, because this is off grid, what you need to do, this is like a norm that you just multiply that total energy consumption by 1.3, because because there could be some energy lost in the system. So just to be in the safe side, you multiply 1.3 of that total consumption that you have get, and that's the energy you need from the photovoltaic system. And here the reason that here I'm just showing that this also depends like the location as well, because with the same size of that photovoltaic system, you won't get like same energy output from that, PV system. Here just I'm showing like, you can see like the same system, like this is what 1 kilowatt, this is 1.5 kilowatt, 2 kilowatt, 3 and 4 kilowatt, and that is in same system. Just for the comparison, install in different city, and you can see that I think minimum here you can see like in Hobart, Tasmania, where like it's not like a sunny state, but you are getting like maximum in Queensland, which is a very sunny state. And same is true for like all the system. So what I'm trying to say that the location also affect like whatever energy you will be getting from that install system. Next, you want to find like what could be that size of the module, because that different size of PV module will produce different amount of power. And to find out the sizing of the PV module, the total peak watt produce needs. So the peak hour, actually again I will say that on the size of the PV module and the climate of site location. So what I'm trying to say here, first you need to know like what sort of PV panels are available in the market and what's their individual maximum power rating that you can get from that particular panel. For example, currently even you can get like 360, 330, 300, and also even like 200, even less than 200. So different sort of size of the panel are available in the market. And as I mentioned, like and also other factor also, we need to consider that the PV modules that will be installing, you won't get, like for example, let's say this is like, for example, let's say you are installing 5 kilowatt system, and for 5 kilowatt system, let's say your sunlight maybe for 10 hours, then it's not something like that you just multiply 5 with 10 and you are getting like 50 kilowatt hour. So that's not the case. So in most of the cases you will get much less than that's the value. And to get that value, in most of the cases for all the city, there is a factor, we called it panel generation factor. So the panel generation factor means what, it is the ratio of what actually you are getting and what you are supposed to get. If you get that maximum 5 kilowatt for 10 hours, what's the energy you should get and what is actually you are getting. And if you just divide, that will give you that panel generation factor, which is different in different location. So what we need to do, that whatever total hour per day we are getting from that PV module, for a particular PV module, is it like either 300 or 330 or 360, we have to divide that particular factor just to get like what's the total peak hour rating actually we need from that PV panel. And then based on that, we have to calculate how many PV panels we need, because definitely the single panel is not enough. So your total demand, like with PCF and that, like what sort of actually real energy you are getting from a particular PV module. And then if you just divide that one with that, then you will get the number of panel that you will be getting. You need to meet your energy demand for that particular location, because if you have got like slightly bit additional energy, fine, but if you have like very oversized and it is not grid connected, you know that you cannot use that additional energy. If you even if you have battery, you can install like certain capacity, but there should be a maximum limit to do that. Next, you need to know, after you finding the photovoltaic system capacity, next you need to find what would be the inverter sizing that you need. And in most of the cases, if you are having off-grid, then your inverter capacity should be slightly higher than the capacity of the photovoltaic system, and it is recommended that it should be like 25 to 30% higher than the total demand that you have in your own house, just to be in the safe side. But if it is grid connected, it can be the same capacity as the photovoltaic system, because you have got the backup when it is grid connected. And also sometime when you have got like a dynamic load like motor, compressor, that sometime, mainly during the starting period, motor current is very high. Sometimes it's like 5 to 7 times higher than the rated capacity. So that is also just to be in the safe side, that it does not exceed the capacity of the inverter, the current that you're drawing. And that's only the inverter power rating. But even if you would like to go further, like what would be the voltage, and even what should be even like is PWM rating and so on, that also you can calculate easily, and I'll show you some example, even if not today, tomorrow. How you can do that is quite very simple. So that's for inverter. So next, if you have a off-grid system, then as I say, like definitely you need the battery. Now, how you can find what size of the battery you need for your particular application? And that is very critical, because that battery is very expensive device. So it's recommended that it should be like as optimal as possible. But even if if you just follow this like normal this analytical way, you won't get the optimal one, but it would be closer. But there are many advanced technique, and I'll show one of them, how you can get even like most accurate one. But this one also give you very close to the one that you need. So again, how you can find the battery sizing. This is the equation that you need to use. So you need to know the total watt hours per day that you need to supply, and how many days of autonomy you want. For example, do you consider that battery should be able to supply your home 2 days, 3 days? So the more autonomy you want, the more expensive would be your overall system. And the reason that we are dividing this two factor, because the battery has also got some losses in the system. So just to consider, the battery efficiency. We are just considering here that, efficiency around is, 85%. And then we are also considering that you won't discharge the battery below 60%, because it is always recommended the battery has got like, like maximum and minimum charge and discharge. So here depth of capacity, like, you can go minimum like, 60. So you will have at least that 40% remaining capacity that you won't, discharge. So that's all you need, I mean, to calculate the, and also like, whatever here the value you get, we also get that, nominal battery voltage we also need here, I mean, to calculate on the battery ampere hour capacity. And the battery we have got like, either like, mostly like a 24 volt or, whatever voltage you have, you just use that one to calculate the battery capacity. So the last component, you also need to a solar charge controller devices as well, and you need to know what could be the sizing of the solar charge controller. So the solar charge controller, again, I mean, is typically rated against ampere and voltage capacity, and it's a very simple expression that, I mean, you can utilize. So we use that short circuit capacity of the PV array, and if this is like, for the series charge controller. So I already mentioned like how we can get the short circuit current for a PV, and when you actually buy any PV panel, if you see the data sheet, it's also written like, what is the short circuit capacity for that particular PV panel. So once you know that short circuit capacity, it is also a norm that you just multiply by 1.3, and that's how probably, I mean, you select your, size of the charge controller. So that's how probably, you can get all of the devices. So the other component you need also like the cables, and you know that there are here like, two part, one is DC and another is AC. AC cable is, like we have been using for so many years. So here the most one, I mean, you need to know the DC cable, because from the solar system to up to your inverter, we use that DC cable. There are also, I mean, different sizes for DC cable are available in the market. For example, 2.5 millimeter, 4 and 6. But in most of the cases, most commonly used one is 4 millimeter cable. And you know the way that we size the cable, depending on the current, just to make sure that, I mean, it does not exceed the capacity of the, rated current of that particular cable. And you already know when you have a PV system, like, what could be the possible current that will flow through that. And as I say, in most of the cases for a residential home, I mean, that's the size is okay, I mean, in most of the cases. And it has got like, negative and positive cables, which have got like, two different colors. And it's not difficult to identify which one is positive and which one is negative. So far, is there any question or comments? Like how we can design a photovoltaic system with battery, inverter, as well as charge controller? Any question or comments? Okay. If there is no comments, I'll move to just show like a example. I mean, how we can do it. So just here, I mean, again, I mean, I already mentioned that you need to find the power for a PV panel or PV string, whatever you say. And that's, I mean, you can do it like in a string. I mean, how many how many modules that's connected in series? Because in most of the cases, I mean, you'll get that module data, and based on the module data, I mean, you'll calculate like what would be that string voltage. And again, it depends, like the voltage of a PV module at maximum power point, and then how many modules are connected in series. And if you just multiply, that will give you the string voltage. For example, here, let's say, I mean, you have got 5 modules and each module is 24 volt. Then, I mean, you will be getting 124 volts for the string. It's just like, simple multiplication. Then, I mean, if you want to calculate the string power, you need to know the string power for a single module, and then number of module, you just multiply it and you will get the power for a string. And once you know the I mean, I already mentioned how you can calculate that one. And then as I said, like for example, for one string, let's say it's like giving 200 watt, and if you have got 10 string, then you are getting like 2 kilowatt power output from that particular array, because array has got number of them, I mean, which is connected in a array string. I mean, we connect number of string in an array. So that's why finally we need to know, I mean, the capacity of the overall whole system. So that's, I mean, we already talked about that, how you can get. But here also you need to know the relation between the DC and AC voltage, because we are using inverter. And you know that, I mean, for a single phase as well as 3-phase, there is a simple expression that you can utilize. For example, if you know that, modulation and also that, DC voltage, you can easily calculate what could be the AC, or even vice versa. If you know the AC that we need, for example, like a 220 or 230, then what's the voltage we need the DC side, based on that, modulation index in your inverter. So either way, I mean, if you know one of them, you can easily calculate other one. But if it is a 3-phase, I mean, there will be another, root 3 term will come here. So here I'm just showing one example. Can I ask you just to read it, everyone? I'm just giving like 2 minutes. So what is shown here, that you have a house where we are just considering like a simple house. This one, it's not like house which have got number of floors. So we're just considering like You have got one 18 watt fluorescent lamp, which is with electronic blast and used for 4 hours per day. You have got one 60 watt fan, which is used for 2 hours per day. And we have got 75 watt refrigerator that runs 24 hours, but with compressor run like 12 hours and off for 12 hours. And the system will be powered by using this PV module. Now you need to design the whole system that I explained previously. So here, I mean, we know everything that we need to design that system. So what would be the first step that I mentioned previously? That first step would be that with your like home, what is the total energy consumption, and how we can calculate that? Again, you just multiply your appliances power rating with the number of hours it's on. So for example, the first one, as I said, like an 18 watt, your lamp, which is on for 4 hours. You have got 60 watt hours fan, which is on for 2 hours, and then 75 watt refrigerator, which is on for 24 hours, but the compressor is on and off like 12 and 12, that's 0.5. So that will give you that you actually need 1092 watt hour per day for that particular home. But in most of the cases, actually, it is more than that for a home which has got, I mean, other many appliances like AC, washing machine, and then your dishwasher and so on. But for that house, I mean, what the total PV panel, I mean, from the PV panel, what energy you need? As I say, like, just to consider the loss that happen, I mean, you have to multiply 1.3. So the PV panel that you'll be installing, from that you need that much of energy per day, like 1419.6 watt hour per day. And the panel that, I mean, we have shown previous, I mean, here. So it only can generate 110 watt by single, and so here again, I mean, as I say, like, whatever the capacity that you will be installing, you will not be getting the same amount of power. So we are just like, on an average, I mean, considering that factor that I mentioned, and it is different for different country. So just like what some countries is like a 3.4. So from that, particular one, we are actually for the peak, I mean, that's the, I mean, watt, I mean, we need during the peak time. So with that one, we have got 110 capacity for single module, and if you just divide that one, so it will give you like 3.67, but you cannot install like that fractional number. So it would be like 4 modules that you need for that particular home. So at least 4 module with a capacity of 110 watt peak time with that particular PV module system. And then same like the inverter capacity is just adding all of your appliances, and then you are just multiplying like with this like either 1.25 or 1.3. So although like your appliance is 153 watt, but inverter should be around 190 watt. for that particular home. And then battery, again, we already know that's what's the energy for that particular battery, and we are considering here 12-volt battery. You can also have like a 24-volt battery as well, and we are considering that we need 3 days autonomy. So using all of this, I mean, you can get that, you know, battery ampere hours, and here this is like, you know, 535 ampere hour capacity that you need for that, you know, particular battery. So it will give you like, you know, 3-day autonomy. But if you want less, then it will be less reliable but more costly. But even if you want more day autonomy, the size should be higher. And in the data sheet, it's already given the short circuit current, which is 7.5 for the PV panel, and just multiplying by 1.3, that will give you, you know, the current of the charge controller. So it's 39 M. So the source controller should be rated like, you know, around 40 ampere at 12 volt or greater. Is it clear to all this example?
Yes, sir.
That's very simple. Again, I mean, there is another example when you have got time. I mean, you can just see this is I'm saying like a grid connected. So for if you have grid connected, I mean, as I said, like, you know, you don't have to use battery. You just need to find out like what would be like the your PV panel and the inverter. So that's all. So the other issue probably you have also heard about that dark curve, which is quite well known for electrical engineer. So you know that, I mean, for photovoltaic system, in most of the cases we get maximum energy from like, you know, 9 to 5. And during that time, you can see here, I'm just showing like some, you know, load demand. But during that time, you know, that our demand is less. And when our, you know, demand is high, I mean, we don't have solar generation during that time. So we need something this time, which has got very high RAM capacity, because here you can see that you need a very high RAM. The battery definitely that can solve that problem with the what I was saying. But if you don't have, then I mean, you need some backup system. In many cases, people also use like, you know, diesel or. But again, I mean, the future solution is not diesel, because we want to get rid of diesel as well. So here, just to, you know, at this time we need like, you know, better control for the battery, just to make sure that it can satisfy that RAM. So next time, and I'll just show you quickly a few control technique. I mean, if someone interested to design. So again, I mean, depending on whether, you know, it is grid connected or off grid, I mean, you need like, you know, different setup control. But at the same time, also, I mean, you can have the switching control as well, which is like one set of control. I mean, it operates when it is grid connected, and other set of component, I mean, it's operate when it is off grid. Now, in most of the cases, I mean, when you have got like rooftop PV, I mean, we want maximum benefit for the PV owner. So that's why, I mean, in most of the cases, we don't use like, you know, this reactive power control. We just use MPPT to get like, you know, maximum. But I mean, when you have got like, you know, huge generation is coming from photovoltaic system, then I mean you need to make sure that I mean the PV does not negatively impact the system performance, mainly the voltage power factor. So that's why I mean in that case I mean your inverter also needs to participate in the reactive power control as well. Like even in Australia, when I mean you have got a very small system, then I mean the grid operator, they does not care. But when you have got a PV system which is more than like a 20 kilowatt size capacity, for those actually the grid operator, they have access, and when there's a need, they can actually immediately shut down from like their control center when they see like that there is some problem it's producing in the system, so they will immediately shut down. So they have got access for that particular PV system. And the reason I mean here probably for the coming years we need both active and reactive power control, so that I mean your system don't have to be disconnected, and it does not hamper the operation of the power grid. So when there is a need, I mean it can supply or consume reactive power. That's why Ibrahim shows yesterday that with that one, I mean you can increase the integration level of photovoltaic system in the network. Because in India it might not happen, but in Australia we already have got some problem in the system with the photovoltaic system. So sometime during the off-peak time, they actually raises the voltage level, and also I mean it has got problem with the power quality as well. That's why they already have said to put that maximum limit for a particular feeder, and that's why I mean there are number of researches going on that how I mean you can improve that integration level, which is also called like the hosting capacity, by using either inverter control or controlling the other devices, for example on-load tap changer, or sometime using fax devices in the system as well. Now for a grid connected system, here you have got three different control. One is active and reactive power control for the inverter, and then your DC link voltage control, and the MPPT that is also coming through your DC to DC converter for when you've got variable radiation. To track that one, I mean we need that in MPPT just to make sure that when the radiation change, still we are getting whatever maximum possible from that particular photovoltaic system. And for the inverter, you can have either single stage inverter or double stage inverter. The single stage is only handle in PPT and PQ control, and when you've got double stage is handle like boost converter handles MPPT, and then inverter handles PQ control. So if you don't have DC, then I mean only you have got single stage, which is does the both MPPT as well as PQ control. And for a real and reactive power control, in most of the cases we use that decoupled control concept. So when it is coupled, like that means if you control active power, it will affect reactive, and vice versa, that if you control reactivity also affect active power as well. But this actually decoupling control sometimes is very difficult to achieve when it is a low voltage where I've got defined sort of R by X ratio. But the concept for decoupled control that so this is the actually the power equation. Like this is apparent power for a three-phase system is 3/2 VD and ID, and this is like a complex power. So that's why you have got plus I and minus I, that is imaginary number. And I mean, if you consider a balanced system, like, all the system are balanced, like all the phases have got, same amount of current, and load connected in the 3 different phases, we can consider that, this quadrature component is 0. And that's how it's actually decoupled active and reactive. So here you can see this. Here this P will be equal to 3/2 VD and ID, and Q will be equal to VD and IQ. So the real power is related to the direct axis component of voltage and current, and reactive power is quadrature axis voltage and direct axis voltage and quadrature axis current, because VQ is already 0. And how we can actually get like VD and ID, again, this is a very old concept, like, the power transformation, which actually generally utilized to convert from your ABC to DQ. And the reason we convert from ABC to DQ, because in ABC we know that all the quantities are time variant, and we have got time variant is very difficult to design the control. That's why we make that axis transformation, which actually convert the time variant quantity to equivalent to DC quantities, which is fixed. The DC does not change with respect to time. And with that one, it's easy to design the control. So that's why in most of the cases when we design the control, we convert into DQ frame. And this is like in a well-known equation that we use. So here, again, as I mentioned, like we just use angle just to shift that, axis from ABC to DQ. So again, D is the direct and Q is the quadrature axis, which has got like, 90-degree phase shift. And again, this is how, like, all the controls that I mentioned work. So here, like, your inverter, which again, as I mentioned previously, we control through this switching pulse width modulation. So what we need actually, we need this 2 component coming in the pulse width modulation. One is modulation, index, like ratio, and another is that angle. And how we are getting that angle and magnitude? So we just need to get direct and quadrature axis component of the voltage. That will give you, like, with square root magnitude. And if you just take like tan inverse, that will give you the angle. And how we get this 2 voltage component? Again, that comes from, like, initially different control. One is coming from your DC voltage control, and another is, which is also like related to the real power as well. Direct axis component of the current, and quadrature of the current is coming from your reactive power control. And what measuring signal you are taking here, like your voltage as well as current coming through here, and here is your DC voltage, and this is your reactive power. Now, in all the system, you have got that PLL, which is calculates the angle, because as I showed previously, you need that angle to convert from ABC to DQ frame. And that's how you get, from the current that's coming here, you are getting D and Q axis component. Then you need some multiplying factor, that's I have shown in the equation. And then throw this to simple, like, PI control. You at the end, you are getting your direct and quadrature axis component of the voltage. And that's how, you can achieve all the controls that I mentioned previously. How we can design all these controls, there are so many different ways available in the literature, but the simple one is the PI control. But if you want all this control, there are so many advanced ways available in the literature, and there are limitation, in the PI control. That's why there are so many research work is going on. Just to find out, like, how we are getting better performance when there is a, different changes happening in the system. And again, I mean, as I shown previously, there are some multiplying factor, and you can see there are some parameters which actually come, in that block diagram, just to show that, like, you need those, system parameter as well. And the control that I have shown in previous cases, PI control, for example, if you want to calculate what could be the gain of proportional and integral parameters, there are also many different ways that you can calculate. And there are simple way people use. For example, one of them is like, root locus method, or, pole placing method. But if you want to do any of this method, the first thing, you need to find that, again, that's like, this is like that, formulation that we need to use, like, x dot equal to ax plus bu. So something like x is the state vector. So with state vector, whatever the matrix is coming, that is A matrix. And with your control input, whatever is coming, that is actually B matrix. So here, this is A matrix, this is B matrix. And from that also, if you want, you can also write that equation this way as well. And this is d by dt. This is nothing but this first derivative. And this is the grid connector system. And where this equation is coming from, this is very simple. If you just use this, to node, and if you apply simple, like, way that you can write that equation for voltage. For example, you know that for inductor, L di by dt, and for resistor is just multiplying IF and RF. So this equation is coming actually here. This is, as I said, L di by dt, that is voltage. This is voltage, and here the voltage is the difference between these two voltages across these two components. So that's how this equation is coming. As I said, like in one of the technique, you can use pole placement technique. So once you know that A and B matrix, and in MATLAB is very simple. If you want to find the pole, or if you want to find the even like the transfer function, and you can easily plot that one, and through your plot you will understand, like, whether your system is stable or not. And even if it is stable, what is the stability margin? And then, if it is unstable, then, by changing the parameter of this, you can shift that one to the, your stable region. And even if it is stable and close to the, stability margin is very less. Also, using those P and I value, you can increase the stability margin as well. But again, I'm not going to that details, because that is more like, standard. And if you want, like in MATLAB, all the codes are also available. You can easily, do that by yourself. So again, this is one of the technique, you can use. But there are many other technique, as I say, like, available in the literature as well. So here I'll just show one more advanced control technique. How you can apply for a photovoltaic system, and then I will finish the part of control. But before that, like, is there any question anyone would like to ask? And even if there is no question, I'll just take like 5 minutes break. And in the meantime, you can refresh your memory. And also, if you need to have a cup of tea, or if you want to go to outside, you can use your 5 minutes. But in the meantime, if you have got any question or comments, I'm also happy to talk to you as well. So, as nobody is asking question, Altaf, is it like,
No question, sir. No question.
is it making sense? Like,
Yes.
to you,
At
or
least I was able to follow.
okay. But if someone is completely outside that field, might be difficult. But as I say, like, currently, I mean, even if you
If
would like,
somebody wants to discuss on a particular topic also, they can just raise it. Some small revision, some question, something that you have not understood.
yeah. And also, I mean, the simple things, I mean, we are not making demonstration, but as I mentioned yesterday, that tomorrow Ibrahim will give a demonstration using MATLAB, how we can use like advanced AI for optimization, mainly for the sizing of photovoltaic system and so on.
That will be very interesting, Professor Jan.
Yeah, so that will be done tomorrow.
Yes.
Because today I just would like to finish all the theory relevant to photovoltaic system. Then it would be easier for him to give the demonstration and understand. And I'll show you that one like the optimization example as well. That will give you some idea, and then when he will give you the demonstration, I think it would be much more clear.
Yeah, this human mind has limited now capacity. There is a lot of parameter for optimization, as you discussed, power supply, this drop, voltage drop, and this. So we can take advantage of AI now.
Yeah, because if you have got like only single or even like one or two
Yes.
parameter you want to optimize, it's easy to do it like during the like in a conventional technique. But when you have got many parameters that you want to optimize, it's better to go for deep learning or neural network or deep learning method.
Yeah, so this is means optimization is the main problem in industry. So we will learn also how to implement this method. Yeah, it will give a lot of satisfaction once somebody will do by their own hand also this type of thing.
Yeah, I mean, I do have, I mean, other MATLAB example as well, but I mean, let's say, I mean, if you want like more demonstration, then I mean, I can organize next week. But first, see like how useful the first one.
Yes.
And then if you see like you would like to see more, I'll try to organize next week.
Sir, I have a question.
Yes, please.
Sir, can we use this PV system for EV battery charging purpose?
Yeah, definitely you can. And there are already so many commercial, and many demonstration, PV battery charge, EV battery charge controller is already in the market as well. And even like, you can design by yourself as well. I mean, it's not a very difficult job. I mean, as I talk, like, the charge controller, that is same. Like, when you charge the EV battery also, I mean, it's like the same way. I mean, you'll be designing the photovoltaic system, inverter, converter, everything to charge your EV battery. Only thing is, would be that, some parameter, I mean, would be different for EV battery, but the process is almost same, and it's possible. And people are also doing, even like masters and even like PhD project on that as well. Because if we use from photovoltaic system, I think that will be the like most efficient way to do it, because you're not transmitting power from long distance. But what you need, that probably even it would be much better if you have another battery with the PV system, not only the EV battery, because if it is off grid, as I said, like, and if you would like to charge your EV battery when there is no PV, at least you can get it from the stored energy in the other battery. So that's why, I mean, we did a project with a shopping center. I mean, I'll show that example again, because I just stopped because I thought, like, you need some PV knowledge when you have got combined application of electric vehicle plus photovoltaic system. So we did a project with a shopping center where we actually designed the system for them. And I'll show you that example. I mean, what sort of structure we have used and how we have done it. So that one also, I mean, we recommended them to have a battery, and we calculate what could be the size of that particular battery they need for that particular shopping center. Because you know that for shopping center, there are so many uncertainty, like when the vehicle coming, when the vehicle is going, how many hours they are staying, right? So there are so many uncertainty. I mean, you need to model just to find out, what sort of capacity or what sort of demand actually will be there. And then based on that, I mean, probably we recommend that, that many charge point you need, and that would be the capacity of the transformer that is connected in the shopping center, and at the same time having another optimized battery as well. So EV actually demand modeling is still, that's a very good topics, because when people model, they actually assume many things which is actually not true for practical condition. So getting like the real model is still, there are some unanswered question, and if someone would like to get the topics, this is a very good topics as well. So anyway, let's start again. The reason, I mean, I stop sharing, because when I sharing, I cannot see anyone, and then when you are talking, I mean, if you see other people, then it's easy to talk. So the next control technique that I'm going to show again, I mean, this is also even like more complex, because if you have a PI control, as I said, like only 2 parameters you can easily design, but as you know that PI has got its own limitation, and even like linear control as well. So if you want to get like, very outstanding performance, I mean, you can go for non-linear control. But to design the non-linear control, I mean, you need to know the control theory and also the mathematical model of your whole system. But the advantage of the nonlinear control, that even if your operating conditions change significantly, still, I mean, your control will ensure stable as well as desired performance for the system, I mean, you are designing the control. But again, I mean, the problem is that your cost would be higher than the simple having like the PI control when you are implementing in the real system. So here again, I mean, I'm just showing like a one grid connected photovoltaic system. So here again, this is PV, your DC link, your inverter, and then as you know that after the inverter we also have the filter. So that's the, I mean, overall system. And the grid is just representing by 3 phases, which is just like equivalent to 3 voltage source. So the first thing, you need to do, again, for any sort of linear, nonlinear control representation, you need to represent the system in this format. Like where X is again the state of the system, which is f is a function of X. Like everything which is relevant to X will come here, and then we have got the control input U. U is the control signal. So anything which is related to the control signal will come here, and Y is your output function, and anything related with the output actually come here. So that's why the equation that I have shown in previous, the system that I have shown in previous here. So if you write down all the mathematics equation here, you will get these 3 equation from that, like ID, IQ, and VDC, which is related to D and Q axis component of the current, modulation index, DC voltage, and also D and Q axis component of the voltage as well. And if you rewrite this equation in this format, this is here X means your ID, IQ, and VDC. So here, if you take this one, the function of X, that you will be getting this one. Like here you can see that first one is ID related, which is comes here, this one. And then the other 2 terms, actually that VDC by L, which is relevant to your control input, modulation index is coming here. So other than that, control input MD and MQ, which is coming here, other parameters is coming f of X. So once you have it, and here as the output, we are having 2 component, ID and IQ axis current. So here we are considering that you have got a 2 input, 2 output system. The input is like your D and Q axis component of the modulation, and output and D and Q axis component of the current. And then finally here, you are rewriting that one like this 2 input, 2 output system like this, where one output is Y1, another output is Y2, one input is U1, another output is U2. And U1 means MD, U2 means MQ, Y1 is ID, Y2 is IQ. Next, if you want to apply nonlinear control, one of the technique, you have to use, because your initial system is nonlinear. So here, somehow you have to transform that system using some different sort of, linearization technique. And one of the technique, you can use like the feedback linearization. That's one of the technique. What it does actually, it is, as I said, it is like a nonlinear control technique, and it transforms that nonlinear system into linear system or several linear system using that coordinate transformation. Here this linearization is independent of the operating point, but for the linearization, nonlinear control, the linearization we done, that is actually depend on the operating point, and that's why this one, as it is independent of the operating point, it's actually provide better performance. And to transform that order of the system, it actually depends on the relative degree of the system. So our original system is 3 order, because here you can see you have got 3 by 3 system matrix. So that's why the order is the system order is 3, but the order of the transform system, that's actually depends on the relative degree of the system and how you can do that relative degree. Again, you have to calculate another function which is called actually Lie derivative. And the way that we calculate Lie derivative is just like we are just doing the partial derivative. We just keep continuing, derivation. For example, we are taking first derivative. Then if it is not equal to 0, then we go for the second derivative. So if it is going first 0 in the first one, that means its order is 1. If it is go for the second one, you can say the order is 2. So that's how we can do that. Axis transformation first, and once we do that, and then we just compare that relative degree of the system with the system of the with the system order, and if both of them are same, we call that system is exactly linearized. But if the rank of the system less than the order of the system, then we call it actually partially linearized. And here you can see when I'm doing derivative for these two cases, we found that the relative degree is 2, but the system order is 3. So that's why the system is partially linearized. It is not completely linearized. And then once we know that one, we convert from original system to that coordinate transformation. And to do coordinate transformation again, there are some equation which is also widely available if someone knows that nonlinear control technique. So you have to use this equation, which is again nothing but just doing some derivative. So once you use that one, actually you are getting this two equation, which is again, as I said, this transformation system is order is 2. So here you are getting two equation in the new coordination. And then so the next one is next things that here in the transform system, we have got MD and MQ, which is actually the control input. So we need to find out what could be their value here. So again, from that equation, if we rearrange, we can write down here. So here for us, everything is known except V1 and V2. And this V1 and V2, actually the main control is coming in the nonlinear system. And there are many techniques actually we can calculate V and V2. And also in MATLAB also there are many system is already available and how you can calculate this one. So as you are not that not all of them are controlled, so probably I'll just quickly go through. And once you got that control, next thing you have to check that stability, that what the system you are designing, is it stable. And to do that again, we just because here our system is the partially linearized, so we have got one equation that we haven't considered in the transform system. So we have to just consider the transform system is already linear, but the system that we haven't considered, we have to just make sure that this one is stable. So once we check this is system is stable, and how we can do this, again we have to find out where that this energy equation, and from that energy equation, once using Z1 Z2 which extends to 0 and t goes to 0, then we found that this is like a 0. So if it is 0, that means so the system is stable, and so our overall system actually would be stable. And then finally we can just write down this V1 V2. As I say, it can be calculated many different way. If you just use the simple PI control, that would be the equation for V1 and V2. And using that one, you just put there and you can easily implement the control. This is the block diagram that you can utilize. So here, again, you have got that your PV unit, DC link, voltage source, inverter. This is the grid point where you are measuring voltage current, ABC to transforming DQ frame. And then here from that control, you are calculating V1 and V2. And from this transformation, you are getting ID and IQ. You are using your feedback linearizing control, from where you are getting M and DQ. And from that, you are again controlling to ABC, which is again coming to at the end your PWM. So again, I mean, everything you are just doing at the end just to find the signal from your pulse width modulation, all the calculation that you are doing. And here also, I mean, I have just again included all the step that you need to do, and I already explained like all of them. So I mean, if someone wants to actually really want to design this one, just follow that step, and if you have got any issue, I mean, you can contact with me. And again, I mean, here, sorry, I forgot to mention why actually we designed that control, because we just found that although, I mean, we would like to operate that control at unity power factor, but in many cases, actually, your system does not operate in unity power factor. And we just make some calculation that if it is not unity power factor, if you have a big, for example, let's say a big solar farm, and you would like to operate at 1 power factor, but instead of 1, if you just do it like 0.9 or 0.95, there is actually thousand of dollar actually you lose if you just don't identify that one. So I mean, here, I mean, the reason that we ask for this very advanced nonlinear control, just to make sure that it's operate like that nonlinear, I mean, it's operate unity power factor. And here actually we compared that performance like with a linear control. And here you can see that, this is like the voltage and current with our one, but this is like the other, just the conventional variable. You can see that there is a phase difference, and if there is a phase difference, so that means it is not operating in power factor. If the voltage and current at the same phase, which you can show that, like the nonlinear current, the red and blue, red and blue, that's exactly, I mean, in phase. But that green line, you can see this is not exactly in phase. So that means there is some phase shift, which means that this is not operating in the unity power factor. And if that is happening, like if you have a small system, the loss is not very high. But if you have a very big system, that it can cost like hundred thousands of dollar loss for a solar farm. So that's why, I mean, you need sometimes you need very advanced control just to make sure that you are getting like unity power factor if you mean to operate in unity power factor. So this is the probably last application I will explain, but before that, is there any question?
Sir,
Yes.
sir, if the PV system is non-linear, why didn't you straight away use some non-linear controllers like robust or SMCs or something, sir? Why would you want to linearize it and then use a linear controller?
Okay, I mean, as I said, like, if you use linear controller, then definitely, I mean, you have to like linearize at a particular operating point, right? And when you are doing that, if your original system is linear, then there is no issue. But you know that when you have got inverter, converter, different sort of switching, also, although I mean here the model that I have shown is not that complex, because we ignored that internal switching that's happened in the power electronics. So even if you consider that model, even it would be more complex. So sometime if you ignore that, I mean, non-linear part, when you are doing linearization, and if you design control considering a particular operating point, and if the operation of that system remains close to that particular operating point, it will give you your desired performance. But sometime if your load changes significantly or some disturbance happens, your operating point will shift significantly from your original. Let's say your original operating point here, and it shifts from there significantly. Then I mean your linear control cannot
won't work.
won't work. So that's why I mean probably you need to go for some either SMC or some advanced level robust, or other way. Even if you want better than that, then you need to go for non-linear control. But better performance if you want, more complex will be your system, and you need like more control effect, and that will also increase the cost of the overall system as well.
Okay, sir. Got it.
And the reason I mean non-linear control better performance, because when you design that, you are not ignoring that non-linear part of the system. You are just considering that in your model while you are designing. And even when you are actually designing different robust control, even if it is linear, what we do, we consider the linear part, but at the same time you also consider some uncertainty. For example, let's say we consider the operating point here, but we consider some uncertainty around that particular point, that we say that okay, this is the original one, but we assume that it will change like something
Somewhere
around
around
that
it.
point. And then we are considering that additional part as an uncertainty, and then
Right.
we're considering that uncertainty, we are designing the control. And in most of the cases, when you operate the control with that robust control, and if it remains with that part, I mean most of the cases it will guarantee the part, I mean your desired performance.
Right, sir.
Any other question or comments? If not, let's talk the last application. I mean I'm going to show now. So this is a standalone PV system, where you can see that it has got DC and AC bus. And DC bus, I mean, again, here we have got charge controller, battery, DC to DC inverter, as well as your PV array. And AC side, you've got like, your AC load. And sometimes you just consider dump load, because I mean, you said that there might be some changes in the load demand. So for this configuration, our intention was to find the optimized size of both the battery as well as the photovoltaic system. Now to do that, I mean, what we did that we collected the load patterns for, I mean, it could be like even for a particular, here we put a particular house for like for all the months in a year, and it was for 3-4 years data. And from that, here, I mean, I'm not showing all the load demand data. We're just showing the here we are seeing like worst case. Worst case means the days you have got very high demand, because at the end you would like to match the maximum demand, because otherwise, if you don't consider the worst case, I mean, the system you'll be designing, that will not be able to, I mean, meet your demand for that particular day. And this is a like upgrade system, so you need to know your worst case scenario. That's in worst case, what's the maximum demand you need. The previous example that I have shown, we're just considering the load like analytical, that load rating, but it is not like if you have a like 4 kilowatt or I mean for example like 60 watt fan, it doesn't mean that it actually consuming 60 watt. It depends on the voltage level and so on. So that's why it's better if you have got that time series load demand. It would be easier to use your optimized value. And here, fortunately, I mean, we got that data, and from that we managed to get like what are the worst case scenario in different months for that particular application. Then again, I mean, this is like first PV module. We already discussed that in previous cases. So yeah, I'm just ignoring that equation again here. And same case of like for the battery as well. Here we are more interested about the SOC. That's why we just initially use the general equation, and the next one it is just like the instantaneous value of the SOC. I mean, you can just calculate by using this equation. And we collected that parameter from that timesheet that PV we recommended for that particular application. So we did have that data sheet for us for the PV module as well as the battery is a charge and discharge operation. Was the maximum depth of discharge that you consider 80%. Minimum SOC of the battery, that's 20%. So all the performance parameter that we have it here, inverter efficiency and everything. And then for the area that we will be calculating size for the same, like the worst case scenario that I have shown previously, for that particular day of that month, we also collected what's the radiation available for that particular house. So this radiation actually is not difficult to find out. There are many like in open source like software available. If you just put that location, it will give you what could be that radiation for that particular area. They also have some prediction for the coming years as well. So we managed to calculate that radiation for that particular day, for the particular month, for that particular area. And then what we did, that deep learning technique, LSTM, which is like currently quite popular, long short memory. So using that, I mean, we just considering that radiation level that's available. We predicted, I mean, what could be that current that we might be getting for that particular PV system. And then as we have the real data for that, we also know what's the actual value, and then we just compare what is predicted and what is the actual value, and you can see that, I mean, it's quite close, the predicted value that we have got from this LSTM model. And this one shows that error that we are getting, I mean, from that model, because you can see that there are some mismatch. And here that root mean square value that was quite low, and this is reasonable while you are using any artificial intelligence or any deep learning technique. So this one again, I mean, we just check the same thing for different months for different technique, and we compare this one with 3 different cases. So again, I mean, we have got that actual, then we just use a simple model, and simple model because I shown you that mathematical equation for the diode, I mean, for the PV system. Using that one, that is called simple model. Then we just use NN, which is got like one like set of layer, like you have got input, output, and then in the middle you have got just hidden layer. But when you've got LSTM, it has got actually multiple layer. So that's how you are optimized in a multiple layer. So that's why in most of the cases, I mean, you expect a better value for LSTM than the ANN. And here, I mean, if you see like in all of the cases, LMSTM is better than simple and I mean simple mathematical model, and then that ANN model. And as I mentioned, like, how we are done it for the same application that I'm showing. Tomorrow, I mean, Ibrahim will give you the demonstration. Now here, we use multi-objective optimization. And here you can see this is our objective function. So the first objective was, because this is like an isolated system, so the first objective was to reduce the loss of load probability. So what does that mean? That we don't want the situation where your overall generation that's coming from your photovoltaic system plus battery is less than your load demand. Because if that is the case, then I mean you will lose your load. And the other one, we optimize the annual total life cycle
Sorry
cost.
for the interruption. Can you please repeat the sentence, sir?
So here we use the optimization function, which has got two parts. One is technical, another is economic. And the technical part here, that we don't want in a situation where your system don't have the capability to supply your load in your home. So when you can't supply load in your home, when your total generation or total power coming from your PV plus battery is less than the total power you need to run all the load in your home. So if that situation comes, you will lose your load. And here we don't want that would like to happen. So that's how we are minimizing that. Another one, definitely we want to reduce not only the capital cost, it is the total life cycle cost, which is capital cost plus other maintenance, labor cost, everything. And the way that it works, so that actually shown in this flow chart. Again, as I said, like, I will give the real demonstration, but the way that actually it works. So initially in the top, you can see that initially we have got the initialization. So initialization means what are all the input parameters here. And here input parameters, we have got the input parameters coming from the PV modules and the battery specification. As I mentioned that we got the specification for the PV as well as the battery. That is coming as an input, because that's the system we recommended for them to use, same system. Then we define the location, load demand, that the LLP value that we want. What's the minimum LLP you want? And here maybe we want like 0.001% or something like that, very small value. And then the cost value that's coming for from them, cost parameters. And then we are also giving input as a solar radiation and the temperature. And from that, using the radiation, location, everything, we are predicting what could be that PV output using that LSTM model that I have shown previously, that what was the PV output current from that LSTM model. Next, what we have done, we use that intuitive method just to find out like the range of the PV and the battery size. Because what happened, I mean, if you consider for your optimization, the range is like 0 to infinite, it will take hours of hours just to find out like what could be that optimal value, because it will take so many iteration to convergence your program. So that's why it's always recommended to find out like the range, like what could be the maximum and what could be the minimum range. In most of the cases, minimum range is not that important, but in most of the cases, we actually oversize. So if we know that limit, then it's easy to fit that in your optimization so that it will only search that optimal value within that particular range. And that will speed up the convergence. And then here we use that multi-objective wind-driven optimization algorithm. But as I said, like there are so many algorithms available in the literature, but this is one of them. Which is also currently popular because it provides quite better performance. I'm not saying best, but better than many of these method. In the literature. And then here actually our multi-objective optimization is done here. So here initially what we did, we check that the current that's coming from initially from PV current and the total load current we need, and then we check whether it is greater than or less than. So once we have like more PV current that your load demand, that's what you can do. You can like use that one either for if you have got like battery, and then what you will do that this is less than that. And then what we do, we check that the SOC level for the battery, because what we do, when you have got additional PV current available, which is more than your load demand, we would like to use that current to charge your battery. But when you'll be charging the battery, when your SOC level is less than the maximum level. So that's why again we are checking that one. And if that is the case, you charge the battery, and again you after charging you are getting what is the SOC level. And here if it is like negative, like your PV current is less than load current, then again you are checking your SOC level, because if it is less than the load demand, that means you would like to use your battery. But when you can use your battery, that it should be SOC level greater than the SOC minimum SOC level. So if that is the case, you will discharge your battery, right? And again, after all that will give you like from that you will calculate how many of these devices you need. So it might give you like that, for example, like 7 PV, 5 battery, or like it could be more than one solution combination, right? So the combination of battery and PV would be multiple. So that's why we need another one optimization, which is like which one combination is giving the minimum cost. And that's why here we are finding all possible configuration with that one, considering that and again if nothing is happened, here we are putting that what's the minimum level we want to not having the power for your load, and then we are calculating all the possible combination and then of the array, and then we are calculating all the cost, and then we are using our multi-objective function. And here you can see that you have got like 2 weighting factors. So you need to decide which one you put more priority. Is it like the technical one or the your cost? So here in our case, we provide more weight for the technical part, 80% and 20%. But based on your requirement, you can select what sort of weighting you would like to do. You like to make it less reliable, more cost effective, or more reliable and costly? So I mean, and again depends your application. For example, let's say you are doing for a hospital application, then it would be make sense to considering like this one giving like higher weighting and this one giving like lower priority, because for a hospital this is a critical load. We don't want like any of the loss of the load, but if it is for like less critical in your home, I mean you can disconnect some of the load which will not affect your quality of life. In that case, I mean you can put more priority, I mean, to minimize the cost. And again, this is just like the definition, what is actually mean by that, LLP. And again, this is the ratio, again, I say like the total energy generated by the system over the total load demand for a specific time of the period. So this is the, energy generated. This is the like, total load demand during that period. And as I said, here we consider 0.01 like in 1%, but based on your requirement, I mean, you can change that, value, and that will also, I mean, affect, I mean, the cost of the system as well. And this is like that, the economic part. And here you can see that we have got number of parameters that we consider in the economic part. Here, the first one we consider like here we have got one is related to PV, another one relates to battery, and then we have got like inverter and battery charger. But other than that, we have got another is other parameter like the installation, your labor cost, and on. And for all of them here, we have got capital plus maintenance cost for all of them. So the cost that here consider maintenance plus your labor plus your like upfront cost that you need to buy your equipment as well. And here again we like giving that cost value in dollar, and here we compared our solution with many of this method that's already available in the literature. So here you can see that I mean our proposed method, like after 10-15 iteration, I mean it got that optimal solution, and it remains the same for the rest of this time. But for other system, you can see that it takes quite a while, I mean number of iteration to get that fixed solution, coming to the fixed solution. So that's why I mean it's giving more like I mean more optimized solution. At the same time, it's quite faster as well. And this table again, I mean just showing like what's, I mean the costing for like different parameter that we have considered, like as I said, like the PV capital cost, maintenance cost, battery capital cost, maintenance cost, replacement cost, charge controller capital maintenance cost, inverter capital maintenance cost, other costs which like circuit breaker, fuses, charge protection, monitoring system support, civil work, and so on, right? So we are considering all sort of costs that's involved, and that's give like your cost, number of unit, total cost, how many years for the payment, discount, inflation, total cost, as well as NPV as well. So all the parameters that we get from output from the algorithm is actually shown here. This one shows again that hourly behavior of the optimized standalone system. And again here we have shown like the current coming from the battery, load current, as well as the battery current. And you can show that the battery charging and discharging actually happen depending on the power, whether it's getting from the, when it's getting the power from the battery, it's charging, and when it's like, it's discharging. And this is just like the defective current when it, that's poverty, that's we mentioned, like, sometimes lot of loss can happen, and this is the probability we have chosen. And the damp current means that when you have got additional current which you cannot charge the battery or you cannot use in your load. And this is the SOC level, and you can see it's also maintain maximum minimum limit. So that will also ensure that it does not have negative impact on the battery performance and also the battery lifetime. Yeah, and we here also consider like that sizing with different optimization techniques that's having, like, maybe most popular one, probably the PSO. So we compared with like ANN, simple model, and then different techniques just for the validation purpose that whatever we are doing, it actually the result is accurate. And you can see like there are some difference, but it's not like when you use like different sort of optimization technology, it will give you some variation, but it's not like that, you have got like a major variation for that solution. So with that, I think this is my last slide for PV technology. So as I already mentioned that there are different sort of next generation PVs coming, and one of them is that floating solar farm, as I mentioned, that is getting popular in different countries, because many countries, like for example, if you consider some country like Singapore, Hong Kong, and also where you have got like so many population like China, compared to the area, if they don't have enough space, probably that would be the better solution for them to have higher percentage of power from solar. And this floating solar farm is exactly that technology which I believe has got enormous potential in coming years. So at present already China, Japan, Taiwan, South Korea, they have got like the capacity of like 2400 megawatt hour. And if you compare this floating solar pump with the individual house, this is actually equivalent to 240,000 household. So you can see that when there are like lots of place, you have got either lake or sea or whatever, you can utilize that one. That will give you opportunity to produce power from solar farm. And if you would like to go that, it also makes sense that you combine floating solar pump with your hydro, because hydro is already there, and you can use that existing transmission infrastructure just to transmit that power from that particular location. It also have opportunity to manage the variability come from solar pump that will be addressed by the hydro. So it will be also like close to your demand center, and you have got water to meet abundance of water to meet the requirement which you need from that combined system. And that will even would be like more energy efficient and more resilient. And again, I'm not going to do like for the civil one, but that's how the system is designed. So on this system is put like on a plastic wraps that actually provides surface for the solar panel to be attached to. just to like keep them safe. So you have like this sort of structure that you can utilize to put your solar panel on top of that. And the global floating solar panel, that's already 652 megawatt. That was in 2019, but it is expected that the next 10 years, so the growth rate would be close to like 30%. So even that is also like another one. If anyone would like to make research, you can think about this technology as well. So with that, I will stop here. But if you have got any question, comments, feel free to share with me.
Jangir, hello. I'm sharing a link with all. This is a power plant, a floating power plant, which has been commissioned near NIT Warangal itself.
So again, same problem, Altaf. We can't, understand you because your voice is heavily broken down. Is anyone else has got any comments, question?
What were the optimization variables considered in your work? You showed a couple of moments ago, sir.
Okay, so the here, the parameter that we optimized, that as I mentioned that to find the right size of the PV and battery, that will make sure that you will not lose any of your load for the off-grid system. And other one, it optimize
Cost.
that's like life cycle cost, not only the initial cost but the whole life cycle cost.
Right.
So that was the parameter it optimized. And for the optimization, the input parameter was like your radiation value, the like your like rating of the photovoltaic system and the battery that you will be using, and that's you can get it from the sheet that you will be supplying when you buy any technology, and then the radiation that we utilize for that particular location. So all of them coming as an input, to your to the optimization.
All right, sir.
Jangir, what I said was, I had just shared a link for floating power plant near NIT Warangal, and one of the persons working there is also pursuing PhD in NIT Warangal.
Oh, that's great. So he's here or he's not here?
No, he is not here.
Okay. But anyways, it's good to know that some of the students, they are already working with the advanced topics.
He is from the company itself, NTPC. He is working there.
Okay.
He is doing his PhD in part time.
Okay, that's good. I hope, later, if you publish anything or having any outcome, please let me know. I'll be very happy to see
Sure.
his research outcome. And if there is no question, I'll leave it here. And thanks everyone again for your time and attention. And I'll see you tomorrow. Thank you.
Thank you, sir. Thank you.
Okay. Bye.
Thank you, sir.
We'll
Okay,
close
bye.
for the day.
Okay.
Thank you.
Thank you, sir.